So we have a matrix here, which we can take as a super simplified financial statement. In a financial auditing, the accountant first sums the values row by row. For example, the first row adds up to 300, the second to 400, the third to 150, and the total of all row sums is 850. Then they sum the values column by column. Say the first column is 300, the second 550, and the total of all column sums is also 850. The accountant sees the total row sum and total column sum match perfectly, and that tells him there are no omissions on the statement, no errors in the subtotals, and it's a valid financial statement. Now here's the question. What if we change this finite matrix to an infinite matrix? An infinite matrix means it extends infinitely to the right and downward. Well, something weird happens here. If we sum the rows, the first row adds up to 1, and every other row adds up to 0. So the total row sum is 1. Now what about the column sums? Well, every single column adds up to 0, making the total column sum 0. The total row sum and total column sum don't match anymore. So what's going on here? Alright, when we are summing up an infinite matrix like this, we first need to use Fubini's theorem to check if the sum is even valid. In Fubini's theorem, we can write the total row sum and total column sum of a matrix as double sigmas. The indices for the left and right double sigmas are just swapped, meaning we are switching the order of summation over rows and columns. And Fubini's theorem states the total row sum equals the total column sum only if the matrix series is absolutely convergent. In other words, the sum of the absolute values of all entries in the matrix converges. Clearly, this matrix does not meet the condition for absolute convergence, so reconciling its rows and columns is completely ungrounded. Fubini's theorem might sound a lot like the rearrangement condition for alternating series, and the rigorous formalization of alternating series rearrangement is actually Riemann's rearrangement theorem. In fact, both Fubini's theorem and Riemann's rearrangement theorem try to answer a crucial question. In the context of infinity, do the most basic rules of associativity and commutativity still hold for mathematical calculations? Let's start with a counterexample for commutativity. Commutativity is one of the most fundamental algebraic rules. For example, A plus B gives the same result as B plus A, so it's easy to assume this rule still applies to infinite series. But let's look at a concrete example. Consider this series. The general term of this series is the reciprocal of a natural number, with positive and negative signs alternating. First, we can use the Leibniz test to check if it converges. The Leibniz test says that if the general term of alternating series approaches 0, the series is guaranteed to converge. The general term of this alternating series is 1 over n, which does approach 0, so this series converges. If we want to know the exact value it converges to, we can use the generating function method. We first write the series in vector form, then compute the dot product of these vectors to get a power series. We then take the derivative of this power series, which gives us a new expression. This is a geometric series, and there's a classic trick for summing this up. When we apply it, we find that the derivative of fx equals 1 over 1 plus x. We integrate both sides, and that tells us fx is log x plus 1. Remember, fx is just our original power series, so this gives us a closed form equation for this series. If we substitute x equals 1 into this equation, we find that our original alternating series converges to log 2. But what if we carelessly apply commutativity and associativity to an infinite series? For example, if we group all the odd terms together and all the even terms together, factor out a 1 over 2 from both groups, then combine the expression, we end up with s equals half s. The only solution to this are s equals 0 or s equals infinity. That's obviously wrong. So even though associativity and commutativity are fundamental algebraic rules, in the context of infinity, we have to be precise about the conditions under which they can be safely used. That's exactly what Riemann's rearrangement theorem clarifies. To understand Riemann's rearrangement theorem, we first need to define two key terms: absolute convergence. A series is absolutely convergent if the series of the absolute values of its term converges. Conditional convergence. A series is conditional convergent if the series itself converges, but the series of its absolute values does not. Our alternating series is a perfect example of conditional convergence. It converges to log 2, but the series of its absolute values is the harmonic series, which we know diverges. And here's what Riemann's rearrangement theorem states. If an infinite series is only conditional convergent, we can rearrange its terms to make the series converge to any real number we want. Take our alternating series again. Say we want to rearrange it to converge to some arbitrary value L. How do we do that? It's simple. First, add positive terms one by one until the partial sum is just greater than L. Let the last positive term we add be 1 over e sub 0. Then subtract negative terms one by one from that partial sum until the new partial sum is just less than L. Let the last negative term we subtract be 1 over e sub 1. Since this is an infinite series, we can repeat this process infinitely many times. The error between the partial sum and our target value L is determined by the last term we add or subtract each time. That's 1 over e sub n. As n approaches infinity, 1 over e sub n approaches 0. So the rearrangement series will converge to L. This is why commutativity and associativity break down for infinite series that aren't absolutely convergent. Changing the order of the terms can make the series equal to any value at all. Now, going back to Fubini's theorem, it's essentially the two-dimensional version of Riemann's rearrangement theorem, and it plays an incredibly important role in the theory of multiple integrals. Alright, that's it for today. We'll pick this up next time. See you later.